Welcome to Manasi Solutions. Today we are going to discuss about connected spaces. When we say that a space X is disconnected, a space X2 is disconnected. A space X2 is disconnected if there exist two non-empty open sets AB such that X equal to A union B and A intersection B equal to phi. Here A and B belongs to what? 2, and both of these are non-empty sets. So if there exists such a pair of open sets AB in 2, then we say that X is disconnected. A space X is disconnected if there exist two non-empty disjoint open sets AB in 2 such that X is equal to A union B. And by using this we can define a connected space. A space X2 is connected if it is not disconnected. A space is not disconnected means if there does not exist such a pair of open sets. So let's define connected space. A space is connected if it is not disconnected, and so the space for that space there does not exist such a pair of open sets. So X is connected if the do not exist open subsets AB and B of X such that A not equal to phi, B not equal to phi, A intersection B equal to phi, and A union B equal to X. For example, consider a set X and to be the discrete topology on X. So every subset of X is open in this space, and let X is a set with more than one point, then X is disconnected. If X contains more than one point, then X is disconnected, because let A be a point in X and let A is equal to singleton A. Since X is discrete space, this belongs to 2, and let B is equal to X minus 2, and this is also a subset of X, so this is also open in X. So these two are open sets and these two are non-empty open sets also, because X contains more than one point. Now A intersection B is equal to phi and X is equal to A union B also. So here we got a pair of open sets which satisfies the conditions for a space to be disconnected. So every discrete space with more than one point is always disconnected. Next, consider a set X and let to be the trivial topology on X. Then there is no any disjoint open sets, non-empty open sets in X with X is equal to A union B. We can't find such a pair of non-empty disjoint open sets in Tau. Therefore, X is always connected. X, any set X together with this topology is always connected. Next, consider the example. Let y is equal to the real line R minus set 0, and it can be written as the union of minus infinity 0 union 0 infinity. And consider the subspace topology on Y, where R is considering together with the usual topology. Then we have minus infinity 0 and 0 infinity R open in R. Therefore, minus infinity 0 intersection Y, which is equal to minus infinity 0, and 0 infinity intersection Y, which is equal to 0 infinity R open in Y. So these two sets are open in Y, and these two are non-empty sets with Y is equal to the union of these open sets. So here, when we consider Y with the relative topology or subspace topology, Y can be written as the union of two disjoint non-empty open sets. Therefore, Y is disconnected. So Y is not connected. So Y is disconnected. Next, consider the plane and remove real axis from this plane. Then we get the set R2 minus R. Here R2 minus R can be written as the union of upper plane and lower plane. And these upper planes and lower planes are open in R2 minus R. And these two, when we consider the upper plane as the set A and the lower plane as the set B, then R2 minus R is equal to A union B, and A intersection B is equal to phi, and A and B are two non-empty open sets in this relative topology R2 minus R. Therefore, R2 minus R is disconnected. Consider the set X is equal to close to 0, 1, union, close to interval 2, 3. And with the subspace topology, of the real line R, and here close to 0, 1 can be written as minus 1 to intersection X, and 2, 3 can be written as the intersection of 1, 4 intersection X. And here minus 1, 2 and 1, 4 are open in R. Therefore, these two sets are open in X. And these two sets are non-empty disjoint open sets in X, and X is equal to union of closed 0 1 union 2 3. Therefore X is the union of two disjoint non-empty disjoint open sets in X. Therefore X is disconnected. And the last example, let R be the real axis in R2 and let A be the point 0 1 in R2, and consider the set X is equal to R union singleton A, and consider a topology tau on X which consists of phi and all subsets of X which contain A. Then if X is equal to A union B, and if A and B are two non-empty open sets in X, then AB belongs to tau, and AB belongs to tau and A and B are non-empty, implies that A belongs to A and A belongs to B. Therefore A intersection B is not empty, that is A intersection B is non-empty. So for any two non-empty open sets A and B with X is equal to A union B, we have a common point A, at least one common point. Therefore X is connected. X cannot be written as the union of two disjoint open sets, non-empty open sets. Therefore X is not disconnected. Therefore X is connected here. Okay. And in this case, here X is connected, and consider the real axis R, which is a subset of X, and when we consider the subspace topology on R, it will be discrete topology because every open set in tau contains all subsets of X which contain A. Therefore for any B in R, the set A B belongs to tau, which is a subset of X, and this subset contains the point A. Therefore this subset belongs to tau. And when we consider subspace topology on R contains the singleton set B, because this is equal to R intersection the open set AB in tau. Therefore every singleton sets are open in the subspace topology. Therefore it will be a discrete topology in R. And when we consider this subspace topology, we have already proved that any discrete topology with more than one point is disconnected. So here R contains uncountable number of elements. Hence we can conclude that R together with this subspace topology is disconnected. Here the superspace X is connected, but the subspace X is not connected, which is disconnected. Okay.